Welcome back to ECE 320A on our special day, 11, 12, 13. I'm leaving that up just for another second, and then we'll scroll down to what we need to do, which homework number 7, I know some of you were very excited to turn it in today. It's due Thursday. It's good if you have it already turned in for today. That's fine. Just remember to bring it next time to class. Homework number 8 will be due a week from today. So you have bang bang on the homework assignments. We'll be covering the material that will get you through hopefully homework 8. I need to make that available. Exam 3 review session, I went ahead and said next week will be the date for that on a Tuesday evening. I don't yet know what the room is, but I've requested one for 6 o'clock. I have something else going on before that time, so that's why it's not the average like it was last time. I think we averaged some times and started at 5:30. This time we're starting at 6 on Tuesday. And exam number 3 is a week before Thanksgiving, which is a week from Thursday. Is that true? A week and a day before Black Friday, if you're into shopping. Good, you're engineers, you're not into shopping. You're waiting for Cyber Monday. That's what you're waiting for, which is the Monday after that. And we'll be in class, but I guess you can bring your laptops or wireless devices if you have to really be in on a particular deal. Oh, we won't be in this class though, will we? Ooh, so don't tell anybody that I told you to do that on Monday after the Thanksgiving break. Today what I want to do is cover how to obtain the sinusoidal steady state. That's what the SS subscript stands for on Y. Finding the sinusoidal steady state from a transfer function and a sinusoidal input x of t, where x of t might be an amplitude at a certain frequency with a certain phase shift. But in general, x of t could be any periodic waveform, because any periodic waveform now has a Fourier series expansion, and if you know how to figure out what's happening with each of those Fourier series pieces or components, you can use this to find your overall output from any generic periodic waveform. This is a powerful approach or technique, and I want you to make sure that it's clear what's going on. We'll go through a couple of examples of finding the sinusoidal steady state output. One starting with a circuit, another maybe somebody gives you the transfer function and they say, what's my output going to be in the sinusoidal steady state? Well, the sinusoidal steady state is going to be reached after an initial transient. And in electrical engineering, sometimes these transients are not very long. They're 5 tau, where tau is the slowest time constant in your system, and that might be 100 milliseconds. 5 of those would be half a second. That's why you spent so much time learning sinusoidal steady-state analysis, because the transients may not be very long, and maybe you're interested in figuring out what's going on in the sinusoidal steady state. We'll figure out how to do that. We'll even show how to do that graphically for you artists or for you draftsmen. You'll be able to sketch this and do it with your dividers and your protractor and figure out what the angles are. You'll be able to add and subtract angles. You'll be able to multiply and divide magnitudes to graphically find the frequency response of your system at a specific frequency omega naught. That's h of j omega naught. Which leads us then to this concept of Bode plots, where you're finding the entire frequency response for all omegas, not just one frequency. That's the Bode plot. I don't think we'll get to Bode plots today, but that's where we're headed, and that's in an appendix in the textbook, the description of those Bode plots, and we'll talk about that in subsequent lectures. Today, let's start by finding how to obtain the sinusoidal steady state output response when you're given a circuit or when you have a transfer function h of s. And all of this is going back to a block diagram that you should feel very comfortable with now. Here is the system described by means of its transfer function, h of s, capital H of s. We have the output, which we usually just represent by the Laplace transform of little y of t, which gives us capital Y of s. And that's going to be produced by some input processed through the system. The system you could think of as filtering or shaping the input to produce or generate the output, y of t. In the frequency domain, and the reason why we like the frequency domain maybe is because there we simply have to do multiplication. We don't have to do time domain convolution. In this discussion, when we're talking about finding the sinusoidal steady state output, we're assuming that our system does enter into a steady state operating condition. The only way that's going to happen is if our circuit, if our system is actually stable. If our system was unstable, as soon as we start shaking it, it's going to start blowing up. It may go unstable and burn up. If it's an electrical circuit, maybe it starts burning up and you go, why is my circuit board on fire? Oh, I made an unstable system. Bummer. Yeah, go see Josie. Get that corrected before you build it again, right? So you need h of s to be stable, and that's what we're simply going to assume. We're going to assume that the system, h of s, is stable. And if I handed you a generic RLC circuit and said, find the sinusoidal steady state response, is this assumption okay? If I give you a generic RLC circuit and I say, find the sinusoidal steady state output response, is this assuming h of s is stable an okay assumption? Or is it true? Yes, it's passive and the resistors are dissipating all of your energy, aren't they? So a generic RLC circuit is stable. So you can validate this, or what do you know about the poles of your transfer function? Those are in the left half plane, aren't they, if your system is stable. So now you have these infinitely tall poles all standing up, or x's, in the left half plane. To get us started, let's just assume a particular input waveform structure. Let's suppose that x of t is a cosine omega naught t plus theta. Whoops, that's not the angle I want to use for x. Let me call it phi. So I'm distinguishing between theta and phi. Theta will come later. What we're going to show is, or we're going to derive the expression for our sinusoidal steady state output. We're going to show then that the sinusoidal steady state output is really just the input's amplitude, A, scaled by the system's magnitude. That's absolute value of the magnitude, not in dB. This is just the number, its magnitude, because h of j omega naught could be complex. We need the magnitude of the transfer function at that frequency that we were exciting the system at, cosine, and if I shake the system at omega naught, what's going to be the frequency of the output? It's a linear system. it's going to be shaking at exactly the same frequency, isn't it? It will have the same phase shift slightly modified by the angle introduced by our system. Have you seen that output response or that equation before? Have you seen that expression before? So if you're given x of t with an amplitude of a frequency of omega naught, and an angle of phi, and somebody says find the sinusoidal steady state of the output, you can now do that if you can compute the transfer function at the frequency in question, which is omega naught. So you find h of j omega naught. That will be a complex number. You'll simply find the magnitude of that complex number. You'll find the angle of that complex number and plug it into this formula. And that's now how the output is responding to that input processed through a given system, capital H of S. If we looked at, so now what we want to do is derive that expression. You won't have to rederive this, but it's helpful to sort of review some of the theory that you've already learned. If I ask you for the complete output response, or the Laplace transform of that, and when I say complete output response, I'm meaning not only the steady state response, but also the transient leading up to the steady state. That's simply this capital Y of S. That's the complete output response in the frequency domain, and that we could generate by forming the product of H with X. And then if we wanted it in the time domain, we would inverse Laplace transform capital Y of S to obtain little y of t. What we're trying to do is avoid all of that inverse transform process. But if this is what we're looking for, and really all we want is the sinusoidal steady state piece, let's now separate the complete output response into two pieces. One is the sinusoidal steady state piece, and the other is the transient piece. The steady state piece is the transform of the sinusoidal steady state response and the transient response is actually the transform of all of those terms in the output expression that are due to the system itself. And we assumed H was stable, so now we have all these S plus 2, S plus 7, S plus 8. All of those poles in the left half plane, they're going to decay, aren't they? They're exponentially decaying, and that's what this second piece is representing. This is now the transform of terms due to all of those poles, and we know all of those poles by assumption are in the left half plane because we assumed H of S was stable. And what we want to do is just find this first piece. Which we can find by inverse Laplace transforming capital Y sub SS of S, but we don't want to form that product and do all of the partial fraction expansions. So without finding the complete or total output response, where that would be Y of t, the inverse Laplace transform of capital Y of S, which is the inverse Laplace transform of h of s, x of s. Let's now derive or develop the expression that we're looking for that I had indicated in red before. So here is now how to find or to justify this expression for y steady state of t. We're starting off with the given information. In terms of structurally, we're saying the input x of t is a cosine omega naught t plus phi. In terms of our tables of Laplace transforms, we usually don't have that angle in there, phi, unless you have a more exhaustive table of Laplace transforms. Typically, you just have cosine omega naught t and sine omega naught t. But we can rewrite this in terms of sine and cosine by using our trig relationships. We can rewrite x of t by breaking up that cosine of two angles. We have cosine omega naught t cosine of phi minus sine omega naught t sine of phi. Or if we just collect that into two little pieces, we have a cosine of phi times cosine omega naught t minus a sine of phi sine omega naught t, where this little piece and this piece with that, let's say, negative sign, those are just numbers, aren't they? And those will just scale the Laplace transform of cosine omega naught t and the Laplace transform of sine omega naught t. So we really don't need to, we'll keep track of those, but we shouldn't get too excited about that extra piece. That's just an alpha and a beta, scaling cosine omega naught t and sine omega naught t. If this is now what we have, what's capital X of s? Here's a review. You should be able to just write this down without even pulling up your transform table, right? You should remember what the Laplace transform of cosine omega naught t is. There's the cosine, and we need to just scale it by this scaling factor, a cosine of phi. And then I'll just drop the negative sign down, and then we have our cosine piece. And again, it needs to be scaled by this a sine of phi. That we should be okay with. That's now what we want to insert or use into our expression for the total output, y of s. Again, we're deriving this. You'll be able to just use the result after this derivation, which was the red line or the red equation to begin the lecture. This now, though, becomes y of s is equal to h of s times that expression for capital X of s, which really shares the same denominator. So let's just write it as a cosine of phi minus a sine of phi omega naught all over s squared plus omega naught squared. Can I factor that? S squared plus omega naught squared? Those are two roots right on the imaginary axis, aren't they? This now factors into a root on the positive, or the top half, and a root in the bottom half on the j omega axis, or on the imaginary axis. So that just rewrites, or can be rewritten, as those two factors. And now we can do a partial fraction expansion in terms of those two poles using complex partial fraction coefficients, K1 and K1 star, which the book uses, and all of the poles in H of S. But all of the poles in H of S, we've already assumed where they belong. This is now equal to y steady state of S plus y transient of S, which is K1 over, and what do we put in the denominator of the K1 coefficient? S minus j omega naught or S plus j omega naught? It's important, isn't it? This one has to be the pole in the positive half of the vertical S-plane. Then we have its conjugate over the other factor, plus, and now we're not going to worry about that. We just say these are just a bunch of stable terms, which will decay with time. These are now stable terms that result from the poles of the transfer function h of s. That's from this picture. Y of s is h of s times this expression that has two pole factors right on the imaginary axis. And h of s, we assumed, had all of its poles. So h of s is a rational expression, and in the bottom of h of s are all these poles in the left half plane, and that gives us this curly bracketed term on the far right corresponding to y transient. And we're not going to worry about that because after how many time constants? 5, it's gone. And all we're left with is those first two terms. What we want to do now is to find or evaluate K1. If we know K1, then we can find that piece that's associated with K1 over plus K1 star over. Let's now find K1. And we're doing this without our calculator, aren't we? Because we don't know a lot of this stuff. But this, how do we find K1? We multiply through everything by its denominator factor, S minus j omega naught, and we replace S with what value do we use for S? It's the value of S that causes that factor that we've just scaled everything by to vanish. But that cancels that factor in the y of s expression. But this is now our pole that's living in the upper half of S-plane that's actually on the j omega axis. Now, if we plug all of that into that expression above, which is now blind to us, but you have it on your paper, so you can refer back to that. That's now K1 is h of s times a cosine of phi s minus a sine of phi omega naught all over what? We've multiplied through by the other factor, s minus j omega, so that's canceled that one And now we need to evaluate this at s equal to j omega naught. Questions on that expression? We're trying to find that unknown partial fraction coefficient k sub 1, which could be complex. And it's just going to be all of this mess evaluated at s equal to j omega naught. And now we can see that evaluating that denominator at that value of s doesn't cause everything to blow up, does it? It's not vanishing, the denominator. It's going to 2j omega naught, which is good. We don't want to substitute something to make things indeterminate. Let's now plug that value for s in to the places that we have identified h of s, or the different values of s. We now have k1 is equal to h of j omega naught. Then upstairs we have a cosine of phi times j omega naught minus a sine of phi omega naught all over and now I'm emphasizing what it is, 2j omega naught. But now we can actually clean this up a little bit if we do the following. What if I now, well, how do I want to do this? Let me rewrite this a little bit. Maybe you can already see what's going to fall out, but let me move that j omega naught in front, and let me, that a is everywhere, so let me pull that a out in front. I'm pulling that a in those last two terms out in front, and so now I have k1 is equal to a, h of j omega naught. That's where that a disappeared to. I now have over here minus, let me say I have omega naught, and then this is sine of phi, all over 2j omega naught. Well, this is kind of nice. I could actually cancel that with that. But I have an omega naught there. But if I realize that this minus, I can write as jj, j squared. Yes. So minus 1 is j squared, or jj. That gives me now one of those j's and that, and I can cancel that with that j omega naught in the denominator. Now I've cleaned up my j's and only have one. And I've converted this now to being a plus j. Is that okay? So that now I have k1 is equal to a, h of j omega naught times cosine of phi plus j sine of phi all over 2. So why don't I, that 2 I don't like down there, so let me pull that out here. So that I now have that 2 there. And that's now my expression. But that should be screaming at us what's in that curly bracket. That's Euler, isn't it? E to the j phi. E to the j phi is this cosine phi plus j sine phi. And now we have an expression for k1. K1 is a over 2 h of j omega naught, which is a complex number, e to the j phi. Let me just remind us of what I said. H of s, or h of j omega naught, in general can be complex. All we're doing is we're taking this transfer function, h of s, and everywhere we have an s, we're replacing it with j omega naught. If we were exciting our circuit with a frequency of 3 radians per second, omega naught would be that 3. And we would then be saying h of j3. And we would plug in j3 everywhere we had the s in our transfer function, h of s. If h of j omega is complex, why don't we now write that a different way? Why don't we write that as a magnitude of h of j omega at an angle? And now let's write that angle. Well, do you know that this theta is not times omega naught? This is a function of omega naught. That's what I'm trying to mean. Where this angle is really just the angle associated with this complex number, h of j omega naught. Is that okay? I wanted to replace in this formula for K1, I want to rewrite this complex number, h of j omega naught, as a magnitude at an angle, or a magnitude at a phase. Doing that, I now have K1 is equal to a over 2 magnitude of h of j omega naught e to the j theta omega naught e to the j phi. Or I can combine those last two, can't I? What were we trying to do? We were trying to find the formula for y steady state. But that was just K1 over S minus J omega naught plus K1 star over S plus J omega naught. If I simply took the K's into consideration into my formula, you could look this up in your table and inverse Laplace transform those two terms. They would now collapse into 2 times the magnitude of K1 cosine of omega naught t. Whoops. Plus the angle of K1. Is that okay? That's just from the table. But now we know exactly what the magnitude of K1 is. That's this piece. And we know what the angle is. That's this piece. Now we can plug that into this first expression from our table. Meaning we now know that y steady state of t is 2 times the magnitude of K1, which was a over 2 h of j omega naught cosine omega naught t plus phi plus theta of omega naught. But we could clean that up just slightly by canceling those 2's. And we now end up with our formula, y steady state of t is a times the magnitude of h of j omega naught cosine omega naught t plus phi plus theta omega naught. where that theta is the angle associated with our transfer function at this frequency, j omega naught. And that's our sinusoidal steady-state output when x was what? X was the original amplitude A, cosine, it's the same frequency, omega naught t, and we started with it having an angle phi, and we had that input when it was applied to a stable transfer function, h of s. Now, if that puts you to sleep, now you need to wake up. Let's just summarize. I didn't see anybody. I didn't have my glasses on, so I don't know who fell asleep, but now you can wake up, right? Now you can wake up and say, I don't know what he just derived. Well, yes, you do. You need to be able to use it. Here are your conclusions. The input that we're assuming is this A cosine omega naught t plus phi. The amplitude of the sinusoidal steady-state output has two pieces to it. It has one piece due to the amplitude of the input, and that gets multiplied or scaled by the magnitude of our system's transfer function, or the magnitude of h of s, when we evaluate that transfer function at the specific signal that we're exciting the system with. This was A, and this was the magnitude of h of j omega naught. That's the first result. The amplitude is just a scaled version of the input's amplitude. And it's scaled by how that system is responding at that particular frequency, how it amplifies or attenuates that particular frequency. The other conclusion is that the phase of this sinusoidal steady-state output is also consisting of two pieces. We have the phase of our input that we started with, except now the phases add, don't they? The amplitudes multiplied, the phases now add, and this is now the phase of our system at s equal to j omega. That was our phi, and this is now our theta of omega naught, which we were defining to be equal to the angle of our transfer function at that frequency omega naught. Now you simply can use this result. If I give you an input, a sinusoidal input, what if I gave you a sinusoidal input x that was actually a sine omega naught t plus phi? How would you use this formula? You could either convert the sine to a cosine, or you could say, I'm going to make my output a sine also, and then just blindly use exactly that same expression with the cosine replaced with sine. It's the same thing. You shake it with a sine, you're going to get a sine out. You shake it with a cosine, you're going to get a cosine out, and they're going to be at the same frequency of shaking as what your input is shaking the system. Let's look at a circuit example. Let's say that somebody gives you an input that corresponds to some voltage, V sub I, an input voltage, equaling 5 cosine of 2t plus 45 degrees. And they want to know what is the sinusoidal steady-state output of the current. I first have to give you the circuit, don't I? So here's your circuit. Here's our input voltage, V sub I, has some impedance, some more impedance, and some more impedance. And you're told that this is the current that they're interested in, and these values, let's say this is now 1 ohm, this is 1 Henry, this is 1 Henry. Boy, we had a sale on 1 Henry inductor, so we have 3 of those in our circuit. And we have a 1 farad capacitor. Good thing they have supercapacitors now, so we don't have to have a football field size circuit in order to implement this, which our capacitor would have been about that big in a classical capacitor for 1 farad. So now you see this football field in front of you. Now we need to put some X's and O's on it. No, teasing. But you can extract X's and O's from this in the form of a transfer function. You can now find the transfer function. So that's the first thing we need. The first thing we need in solving this is we need H of S, where H of S is this transfer function between our input and our output, I sub 0. How might we find that transfer function? Given this circuit, how would you analyze that circuit? Probably your first thought might be, oh, that's a mesh problem. Write some KVLs, write 2 mesh equations. That's valid, that's true. And your second mesh, or that second mesh current on the right-hand side mesh, would be I sub 0 of S. And you could then solve for I sub 0 of S in terms of V sub I of S, take that ratio, and there's your transfer function. Let's do it another way. Let's do a source transformation. Put everything into parallel. Then we just have one unknown. If we did it in mesh, we would have 2 mesh currents, and we would have to do one of those silly Kramer's rules with ratios of determinants, right? Or you could plug it into your calculator and let your calculator do it. Fine. That's true. You could do it that way. Maybe not your 4-function calculator that you got on a blue light special at Kmart, but you're shopping on Black Friday, which allows you to purchase one of these high-powered calculators and then do a crash course in trying to learn how to use it before the final. What if we do a source transformation? Now we want to take this impedance. We have a Thevenin right there, source and impedance. We can turn that into a Norton equivalent as a current source in parallel with that impedance. What's that impedance that I've highlighted in yellow? SL plus R, right? S times 1, S plus R. R is 1. Oh, that's easy. S plus 1, isn't it? That's our impedance. We can now rewrite that circuit with a source transformation and end up with the following. We now have a current source We have a resistor and an inductor. We have a inductor and a capacitor. And we have another inductor and capacitor. This was 1, this was S, this was S, that was S. Remember we had that fire sale on inductors, 1 Henry inductors. So there's SL 3 times. We had a 1 farad capacitor, 1 over SC. That gives us 1 over S. And this second one was 1 over SC, 1 over S over 2. That 2 can go upstairs, and we now have 2 over S. And what we were interested in was this particular current. What I have failed to do is write the expression for that current source, which is source transformation. That's our original voltage divided by the impedance that we used. Is that okay? And now we simply have one unknown. We only have this unknown voltage at this node, let's say V sub 0 of S. Instead of 2 unknown mesh currents, we now have 1 unknown voltage, node voltage. Now we just have 1 equation to solve for. And then we don't have to do this Kramer's rule stuff. If we write KCL for this circuit, we just have the algebraic sum of those currents at that node. We have going in, we have V sub I over S plus 1 equaling all of these currents flowing out. We have V naught over S plus 1. We have V naught over S plus 1 over S. We have V naught over S plus 2 over S. Is that okay? That's just going to give us some mess scaling V naught and V sub I. And you can do that algebra. If we have V naught, then we can create an expression for that current. I naught is just that V naught divided by that impedance in that rightmost leg of our circuit, which is now V naught of S over S plus 2 over S. But if I get rid of that denominator of a denominator and put it upstairs, I now have S V naught of S over S squared plus 2. I'm going to let you go home and do the algebra to find V naught of S. So you could even plug that into your calculator, I guess. Remember that cartoon that you've always seen that this crazy professor's up the blackboard or whiteboard? It's probably a blackboard. It's such an old cartoon. Probably didn't have whiteboards. Have this big mess of equations, and then you see this bubble that says some magic occurs. Well, some algebra to finding V naught of S. Here's the magic. It's not magic, it's just algebra. But now we have H of S is going to be this ratio of our output to our input. That now ends up being S times S squared plus 1 all over 3S to the 4th plus 2S cubed plus 6S squared plus 3S plus 2. Now, does that even look like it might be correct? Okay, the comment was it was a fourth order denominator. It's a fourth order system, isn't it? The transfer function is fourth order. So what? We had 4 energy storage devices in our circuit, didn't we? We had 2 capacitors, or no? Yes, we had. Whoa. So we had some cancellations, didn't we? So we had 5 energy storage devices. So we're just going to say that that's true, and the algebra is correct. I did it both ways. I did it with mesh just to check my algebra today, and then I had done it earlier with this node voltage. So it's a little bit different than maybe what we could have expected, right? We would have maybe been anticipating a fifth order denominator. But we've had a cancellation. Where are my zeros? Do I have any finite zeros? I have a 0 at the origin, don't I? What else do I have? Then I have 2 on the imaginary axis. Does that mean my system's unstable? Zeros don't matter, do they, for stability? Zeros can matter in the system. If you've got a bicycle, where's one of your zeros? It's in the right half plane, isn't it? But that's okay. In this case, you would need to factor this denominator because we don't have one of those present and positive results for a fourth order. Now, if somebody factored that into 2 quadratics and both quadratics coefficients were present and positive, we would be happy. It would be stable. If you factor this, you'll find that you do have poles in the left half plane. Maybe they're not that far into the left half plane. We have one at 0.0151, or one pair, plus and minus j 1.245, and another pair at minus 0.318. That's a little further into the left half plane. Not quite so far up in the vertical direction at j 5.73. If I now said, oh, that particular circuit, remember I was talking about football fields? Are zeros, and if I said sketch the pole 0 pattern for that transfer function, you would say, oh, there was a 0 at the origin. Whoops, I was intending that to be a different color. I'm going to have to give my tablet an impulse response, and then we may have to stop lecturing. Then we had zeros at plus and minus j1, didn't we? And now I said that we have poles really close. That's 0.015 away from the vertical axis. And then we had some that are a little bit further out and down in terms of vertical distance. That's now the pole 0 pattern for that particular transfer function. 4 poles and 3 zeros. Is the system stable? Yes, not real stable because those are getting close to right on the imaginary axis. If they were on the imaginary axis, what would happen to that system? You would have no damping in those particular modes. So if you kicked that system and got it started, it would never stop, would it? It would be an oscillator. There would be no damping. All right, now what did we have? Now we've derived h of s. There's h of s. We can now use that. Remember where we started? We were supposed to be finding the sinusoidal steady-state current through that last branch in our circuit. Remember that voltage. we now have an input, v sub I of t of 5 cosine of 2t plus 45 degrees. And we are wanting I sub 0 steady state of t. What do we need to complete this exercise? Can I find the sinusoidal steady state output current now more quickly than when I started? I hope so, since I spent so much time deriving that transfer function. Sometimes you just speak before your head kicks in, huh? We weren't wasting any time, were we? You were learning. That was a good exercise. All right, so what do we need? We need h of j. Whoops, let me do this in more steps. We have h of s, but we don't need all of h of s, do we? We just need to know, how is that system behaving at a given frequency? And what frequency are we interested in? We're interested in 2 radians per second, not 2 frequencies, the frequency of 2 radians per second. So we now evaluate, whoops, our frequency is now 2. We need h of j2. And we can find h of j2 if we simply go back to h of s, and everywhere we find an s, we replace it with j2. We had an s times an s squared plus 1 squared, didn't we? In the numerator, we had s times s squared plus 1. Downstairs, we had 3 s to the 4th plus 2 s cubed plus 6 s squared plus 3 s plus 2. And now we simply perform some complex algebra, or algebra with complex numbers. It's not complicated, it's complex. This now ends up being minus 6j over 26 minus j10. Or h of j2 is a complex number, isn't it? It has a real part and an imaginary part. If you do the math or the algebra, you end up with 0.0773 minus j 0.201. And that's how the system responds to a sinusoidal excitation at 2 radians per second. It has that response, which says, oh, maybe an easier way to think of that is, why don't you just tell me what the magnitude is at a particular angle? And you can compute the magnitude, the absolute value of that complex number. It better be a little bit bigger than 0.2. It's actually 0.215. And where's the angle? Which quadrant is the angle in? Can you tell by the rectangular form of that complex number? So now if you're visualizing where you're at, you now are walking which way in the horizontal direction? Positively or negatively? Slightly in the positive, aren't you? And then which way are you turning? Up or down? Negative. So which quadrant are we in with the angle? 1, 2, 3, 4. So we can play Foursquare. I won. Nobody responded. Where are we at? We're in the fourth quadrant, aren't we? So this should be a negative angle, and it's actually minus 69 degrees. Can we now use that information? Yes, we can. Now we know we had our original amplitude 5, but it's now attenuated by 21%, isn't it? 0.215 at that frequency of that circuit. Cosine, we shook this system at 2 radians per second. It's linear. It's going to be shaking at exactly the same frequency. It's now 2t. It started at an angle of 45 degrees, but now we've modified that after passing through the system by minus 69, which says then that our sinusoidal steady-state output current is a little bit bigger than 1, shaking at the same frequency, now with a phase shift of minus 24 degrees. Questions on that? Yes. Where did the 2J come from? Is that what the question was? How did we get J2? We derived, so the J, we need to evaluate our transfer function on the imaginary axis. We're walking under the circus tent. Now we just need to know, where do I stop? Where do I stop, and then look to see what's my magnitude of the circus tent, what's the top, and then I have to compute the angle. Well, the distance I walk up that imaginary axis is based on how fast I'm shaking that system at my input, isn't it? My X was at 2 radians per second. That tells me I have to walk up to J2 and look around, find the altitude of, or the elevation of my circuit tent. That's the magnitude and the angle at J2. So 2 is the omega naught, the excitation frequency of my input. If I gave you a frequency, if I gave you an input of 5 cosine of 10t, then you would evaluate h of s at J10, s equal J10. Okay? And we derive that result. So now you'll want to go back and just enjoy that result. We can now use that all the time. What if I now looked at a transfer function? Now we're not spending any time trying to find this. Somebody has just handed you this. Maybe it came out of a network analyzer or a spectrum analyzer. Now they say you have a transfer function of 1,000 s plus 5,000 over s squared plus 6,000 s plus 25 times 10 to the 6th. That's our transfer function of our system. Now let's say that somebody has given you an input that they're exciting the system with, and they say x of t is 120 cosine of 5,000 t plus 30 degrees. And you want to know, what's the output? What's the frequency of the output going to be? If you couldn't do anything, if you had 10 seconds left on an exam, you could say y steady state of t will have a frequency of 5,000 radians per second. And it will be scaled, it'll scale 120. And I don't know whether it's going to amplify or attenuate that 120. It's going to depend on what? It's going to depend on the transfer's behavior, its magnitude at J5000. Whoops, I'm answering too many questions. Can we apply that formula to this? Why? H of S is well behaved, meaning it's stable, isn't it? How can we confer that or confirm that? What do we need to do with the coefficients of the denominator polynomial of capital H of S? Both of those coefficients, the coefficient of S and the constant, have to be present and positive. If they are, it's in the left half plane. So we now have H of S is stable without even having to buy a fancy calculator. And that's because these coefficients in the denominator they're present and positive, and that's only true as long as we had second order factors. If it was a third order, that's not a sufficient condition for being stable. It's only it's a necessary condition. All right. So now, what frequency do we need to focus on in finding the output response? That's the frequency of our input excitation, isn't it? If that's the case, then what do we want here? H of J, 5,000. It sounds like a computer or something, or a car, HJ 5000. But we're in an electrical engineering class, so this is a circuit, isn't it? Maybe. We don't know. H of S could be a lot of different things. We just were told it was a transfer function. But now we simply replace S everywhere with J 5000. What's the angle of our numerator? -45 degrees, isn't it? And we have 5,000 times 1,000 times the square root of 2, because they're equal real and imaginary parts. So we have 5 times the square root of 2 times 10 to the 6th at an angle of 45 degrees. Downstairs, it's obvious that that was 30 times 10 to the 6th at an angle of 90 degrees. Maybe the magnitude's not so clear. Well, it is, isn't it? Because 5,000 squared is 25 times 10 to the 6th. And that cancels the constant, and then we have 6,000 times 5,000, which is 30 times 10 to the 6th at an angle of 90 degrees. This now says that we have, for the transfer function, H of S, that's the square root of 2 over 6 at an angle of -45 degrees. And we can now use that to find our sinusoidal steady state. Our sinusoidal steady state is the amplitude of our original signal scaled by that magnitude of our transfer function, square root of 2 over 6. Cosine, we better be shaking at the same frequency that we started shaking it with, which was 5,000, plus 30 minus 45, or our sinusoidal steady state output is now 20 times the square root of 2 cosine of 5,000 t minus 15 degrees. Questions on that? Now what we want to do is see if we can do this another way as far as evaluating H at a given frequency graphically. if we go back to that example, our transfer function is now 1,000 s plus 5,000 all over, and if we write this in a factored form, we can write it as s plus 3,000 squared plus 4,000 squared. Is it clear now where our poles and zeros are? Let's scale this up by 10 to the 3. This is now our S-plane. So here's J1000, J3000, minus J2000, and here's minus 5, minus 3, minus 1. Where do we put some of these X's and O's? And here's J5000. Where do I put my zeros? That's over there at minus 5,000, isn't it? Where are my poles? It's minus 3,000 plus and minus J4000, isn't it? And now what I want to do is I actually want to find my H of J5000, so I want to evaluate when I'm standing at that spot underneath my circus tent, at that triangle. I'm walking up my imaginary axis until I reach J omega naught. Omega naught in this case was 5,000. That was how fast I was shaking that system. That was my X of t. Now what I want to do is figure out how these singularities, these poles and zeros, contribute to the magnitude and phase at that triangle. What I'm going to do is actually draw lines and angles from each of those poles and zeros to that triangle. Meaning, my angles are going to be measured with respect to a horizontal line going to the positive, in the positive direction. And this pole is that far away. And I'm going to label that as L sub P1, and it's going to have an angle to that point of theta P1. This pole is further away, obviously, and it has a length of L sub P sub 2 at an angle of theta P sub 2. And this zero has a length of L sub Z and an angle of theta sub Z. And what I can actually say is that H of J5000 is going to be that original gain. Now remember, this transfer function is actually in pole zero form, isn't it? So I now have 1,000. I have to keep track of that gain, but now I have the length of my zero at its angle. That's the complex number of that zero factor. Then I have the length of the first pole and its angle, and I have the length of the second pole at its angle. And now if I want the magnitude of H of J5000, I simply have to take that 1,000, multiply it by the length from the zero to that triangle, and divide it by those two lengths from the poles. So my pole distances I'm dividing, my zero distances I'm keeping in the numerator. And my angle is going to be the angle of the zero minus the sum of all of these angles in the denominator. And that's how I can numerically, or constructively compute or graphically compute the value of a transfer function at a given frequency from the pole zero diagram. My transfer function needs to be in pole zero form, and I start measuring length. So if you still have your dividers from your drafting class, probably don't even know what I'm talking about, do you? Everything's done on a computer now, isn't it? So now you draft on your computer, but we used to have these dividers. And boy, those hurt when the instructor would throw them at you and they'd stick because they had just two needles on them. But you could measure distances, and you could get out your protractor and measure your angles. So now you need to sketch accurately, and you could measure all of this information from a transfer function. We'll pick up at that point on Thursday.